So we start with ek plus 1, xk plus 1 minus x star. So now we can plug in our expression for xk plus 1, and xk plus 1 is xk minus f of xk divided by f prime of xk, and then this is all minus x star. Now, we already know that we can express ek as xk minus x star, so we have xk minus x star, so we can just call that ek minus f of xk over f prime of xk. And so then what we get from there, I'm going to factor out this 1 over f prime of xk. And then I'm going to use the second Taylor polynomial expansion of f of xk. So that's going to give me f of x star minus f prime xk x star minus xk minus 1 over 2 factorial of just 1/2 f double prime of eta k xk minus x star, and then close that bracket. Where eta k is just a point between xk and x star. So now we're going to try to simplify this a little bit. So I'm going to distribute this term throughout. I'm going to scoot over a little bit too. ek is minus f of x star divided by f prime of xk, and then plus f prime of xk x star minus xk all over f prime at xk, and then we have plus 1/2 f double prime of eta k xk minus x star. This is all over f prime of xk. Alright, so now we want to try to simplify as much as we can. See that those two cancel right there. F prime, or f of x star, well, what is x star supposed to be?
F of x star should be 0.
Right, f of x star should be 0 because x star is supposed to be a solution. So if we plug the solution in, we should get 0. So this term cancels. That goes away.
Isn't there a square?
Yes, you are right. Square right there. Thank you. Okay, so we've got ek, and then this term cancels, and then here we have left plus x star minus xk, and then plus f double prime of eta k xk minus x star squared all over 2 f prime of xk. So simplified a lot, but there's still a little bit left to do. Here, this, so this looks similar to our expression for ek, but it's, right, so we can pull a negative sign out. So we've got e to the k minus, and then that's going to be negative x star plus xk. So now we've got ek minus, and this right here is equal to ek. So those cancel each other out. And then what we have left is f double prime prime of a to k xk minus x star squared all over 2 times f prime at xk. And actually this right here, xk minus x star, we can replace that with a to k because that's some point in between these two. No, wait, I'm sorry. No, I'm sorry. No, this right here, xk minus x star is what?
EK.
Right. So that just becomes EK squared. So now, we finally worked this out. I'm going to rewrite it over here so it's not quite as messy. So we've got f double prime of a to k over f prime of xk times ek squared.
2 on the bottom.
Oh yeah, thank you, Teresa. Alright, so for each, because for each k, a to k lies between xk and x star, then a to k converges to x star as well. And then by the continuity of f double prime, we include that Newton's method converges quadratically to x star. So the asymptotic error constant for Newton's method is the absolute value f double prime of x star over 2 times f prime of x star. So now we've come up with the asymptotic error constant for Newton's method.
So since the coefficient is squared, it will this quadratically, right?
Since the coefficient is squared,
Or since it has a double prime, right?
well,
Right.
not necessarily because we have well actually, converge quadratically just means how many decimal places of accuracy that we gain each iteration.
Okay.
So, like in this example, you can see how many decimal places of accuracy we gain from one iteration to the next. So now we're going to take a look. Another thing about Newton's method is that it loses its quadratic convergence when we have a double root. Now, in any root finding problem or any root finding method, then we're going to have problems at double roots. And this is with Newton's method just the same. The asymptotic error constant becomes infinite, and therefore the quadratic convergence is lost. And we're going to take a look at what happens there. Now,